Welcome to this lecture series in group theory. We will be discussing more about the order of an element in this lecture. Last time we defined the notion of order. So if G is a group and X is an element of G, then the order of X is defined as the minimum natural number n, the smallest natural number n, such that this holds. And there may not exist any natural number such that this holds, in which case we just say that order of X is infinite. So truly speaking, this statement should be qualified with a warning that if this is a non-empty set, then order of X is defined in that fashion. If this is an empty set, then order of X is denoted by the symbol infinite. All right. So regardless of whether order of X is finite or infinite, we saw that this equation holds, where this denotes the subgroup generated by X. This is the cardinality of the subgroup generated by X, and the order of X is just the same as that cardinality. All right. We saw that if order of X is finite and n is some integer such that this holds, then order of X divides that integer. Also, if G is finite, then order of X divides the order of G, where order of G just means the cardinality of G. This is because of Lagrange's theorem and this observation, because order of X is just the cardinality of the subgroup generated by X, and by Lagrange, this of course holds, because after all, this is a subgroup. So this is a straightforward implication of Lagrange's theorem, although it's not obvious immediately from the definitions. All right. These are the problems. And now let us prove the main result of this lecture. So G be some finite group, and X be some arbitrary element in the group. Fix a positive integer k. Then we want to say that the order of X to the k can be calculated if you know the order of X by this formula. So here we have a GCD appearing and whatever. So this is the formula by which you can calculate the order of the exponent of something whose order you already know. All right, so let's prove this. So let D equals the GCD of order of X and K. Say order of X is dA and K equals dB for some integers, for some natural numbers in fact. And note that A and B are relatively prime. Okay, so there's nothing much going on so far. So now what we want to show is the following. We want to show that it's a very crazy W. Want to show that B, or rather not B, sorry. We want to show that order of X to the K is A. So this is what we want to show, because this number is nothing but A. Order of X is dA divided by GCD is D, so that is A. This is our aim. So now let n be some positive integer such that the corresponding exponent of x to the of x to the k is identity. Okay, so then x to the kn is identity, which implies that order of x divides kn. So if this happens, then this happens. Okay, which implies, just changing notation, that dA divides dBn, which implies A divides Bn, which, since A and B are relatively prime, says that A divides N. Okay, so therefore in particular, N is greater than or equal to A. Right? But it is clear that x to the n to the power A equals x to the Ka equals x to the dBA equals x to the dA to the power B, which is equal to x to the order x to the power B, which is identity, because x to the order x is identity. So thus order x to the power k is less than equal to a, right? Because if you raise x to the k to the power a, you get the identity. So order of x to the k cannot be more than a. But this deduction here says that order x is at least a. So let me highlight that. This whole thing showed that order of x to the k is at least a. Because if n is some positive integer for which this happens, then we showed that n is at least a, and therefore order of x to the k is at least a. So if we combine these two deductions, we will find that order x is indeed a. Sorry, order x to the k is a. And that's it. That's what we wanted to show. So it's not a difficult proof, but this result is important. Okay, this is a very nice corollary, although the proof of it has already been in some sense given in the previous argument. So G be some group and X be some arbitrary element in G. Assume G is finite. You can just assume that the order of X is finite, but let's just say G is finite. Okay, and yeah, so K be some positive integer which is relatively prime to the order of X. Then order of X to the K is same as order of X. And if we apply the previous proposition, this is immediate because order x to the k is order x divided by GCD k and order x. That by hypothesis is 1, so that is order x. So it's immediate from the previous proposition. But this should be intuitively very, very obvious. Okay. So this was a short lecture, and I will cover more things about order in the next lecture, and we will prove a very interesting theorem due to Cauchy, or a special case of that theorem due to Cauchy. Anyway, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.